evening. Welcome to the QCIS channel. Where on this channel, you get a daily dose of science, technology, engineering, and math. My name is Leon Jones, and tonight I'm going to get into some science and land surveying. And I'm going to talk about GPS, which is Global Positioning Systems, and the Global Navigation Satellite System, that's known as GNSS, and it deals with different receivers, Trimble mixed receivers, RTK, and what the receiver does, receives signals from satellites, and you take your information and you mark your points. You can get your height of instrument, can even get your accuracy. And this is the science of land surveying. A long time ago, when you dealt with land surveying, you had a plumb bob, you had 3 and 4 man crews, you had a steel tape, which we called a chain, you had a theodolite. Then we start to get more into the electronics with the top con equipment. Now, if you look at it today, we're actually involving a lot of GPS, remote sensing, Google Earth. In fact, if you look at the background that's created, guess how that background was created? I created that background. Now, how did I create that background? Well, I actually utilize Google Earth, and Google Earth is a good tool. It is free. So basically, what I did is I was given a KMZ file. I uploaded that KMZ file. And what I did is where you have all of those areas that have red pins, well, I took a segment of road and I actually marked all the control points, like the center line of road, your PCC, which is your point of compound curve, your point of reverse curve, that's the S curve, that's known as the PRC, and your point of curvature. And these are the points that I created so I could create an open network of control points. And it is very important that control points are placed accurately, because when you do any type of land surveying, you're going to go off of control points. This is why you want to make sure that your control points check out correctly and they're positioned correctly, such as if you're doing a road, want to keep everything in the center of road. So if I were to create a network or a path, that line would actually follow that road to the center. And if I wanted to utilize these points, I could create developments from these points. And with these points, I can put other control points in. But these points were actually established. I could have gone out there with a receiver, turned on the data collector, put everything in there. You have a Trimble, you have a lot of data collectors that can do this. But surveying now, you don't even need many crews out there. In fact, you need 2 people. One guy actually doing the legwork for you by putting the laths together. The laths are the stakes, marking the laths, putting the tape, go out and stake it. Now, there are times where you're going to send somebody out there, you're going to have a prism, but you can set a robotic instrument up. But GPS is what everybody's going to. Now, GPS and GNSS, GNSS and GPS, they were established by the military, and I know NOAA, the National Oceanographic Atmospheric Administration, they also use a lot of this data. In fact, there's a website where you can pull data from NOAA, the points from any state. So what I'm going to do, I'm going to share my screen, and I am going to give you a definition of what GNSS is. Now, GNSS stands for Global Navigation Satellite System, which is a general term for any satellite-based system that provides autonomous geospatial positioning with global coverage. These systems use a constellation of orbiting satellites to transmit signals that are basically they're receivers on Earth that can determine their precise location and time. Examples of GNSS include the US-based GPS, Russian GLONASS, European Galileo, and Chinese BeiDou. Now, here's how it works. Satellite signals. Satellites in the GNSS constellation transmit signals containing data about their location and their precise time the signal was sent. Then the receiver measures time. So you have a GNSS receiver on the ground, measures the time it takes for the signal to arrive from multiple satellites. Then there's distance calculation. It's where the receiver calculates the distance to each satellite by multiplying the signal's travel time by the speed of light. Notice speed of light is 3.00 times, I believe, 10 to the 8 meters per second. Then you have your trilateration. Now, your trilateration is you combine the distances from at least 4 different satellites, and the receiver can determine its exact position in 3-dimensional space. And we're talking about longitude, latitude, and altitude, and of course, the precise time. Now we have common examples of GNSS. I just mentioned to you a minute ago, GPS is what we have in the United States. That's the global positioning system. It's the American system, which is often used as a generic term for GNSS, though it is just one of many systems. Then we have the GLONASS. That's your Globanaya, Navigacionana, Spatukovaya Systema, which I did pronounce that pretty good. That's Russian. That's their system, the navigation system. Galileo, it's a European navigational system. BeiDou, that's the Chinese navigation system. Then you have GNSS technology. It's used in a wide variety of applications. Navigation for cars, boats, aircraft. You can even download a GPS app on your phone. In fact, I did it and went out with my own phone and took some points. It's good for tracking vehicles, pets, and people, scientific research and surveying, telecommunications and emergency response, agriculture for precise field management. Now, I'm bringing this topic to the table right now because when we deal with surveying today, we're also dealing with geomatics. And within geomatics, we have GIS. That's the Geographical Information System, which a number of geography majors take it, and you create a lot of maps, like Google Earth. Like you see this map that I created, not very difficult, using it for my background. Now, I'm going to share my screen, and I'm going to get to a presentation. And this presentation is, it's the GNSS GPS Basics. This is by Vince Cronin of Baylor University and Shelley Olds of Univaco. And this was out in 2019, 6 years ago. But this has become very, very popular in land surveying. And this is basically where I'm going with it from the land surveying part. And if you're going to take a land surveying curriculum, you're going to have some geomatics, GIS. So without further ado, my My screen is on, and I'm going to get into the PowerPoint here. So, I'm going to describe the navigational satellite system, GNSS, and how it enables positioning. I'm going to distinguish different grades of GNSS receivers, their uses, and their accuracies. Highlight applications of GNSS in the geosciences. Okay, what you see out here are GPS receivers. They're all around us. Now, here's the one that I used when I was outside. Now, you see, this is the receiver, looks like an RTK receiver, and it's the data collector. And what you do, you set this receiver up, maybe about, I'm going to say 6 meters up. You put that in a data collector, and you basically go to the data collector and you name the point. And then you have your Garmin. That's a GPS receiver. Your phone, that's GPS. And you also have even your cameras. That's also GPS. Now, again, GPS is not new. The military use GPS. NOAA uses GPS. But we're doing a lot of map making, and we're utilizing a lot of photogrammetry and remote science as well. All of this goes under GNSS and GPS. Okay, GPS provides 3D positioning. Positions on Earth can be reported by using Cartesian coordinates that's relative to the Earth's center, geographic coordinates, lat, long, elevation in degrees, and projected coordinates. That's the UTM, state plane, inches, meters, or feet. And you can see what it looks like when they take the Earth. Now, if you look at the Cartesian system, where generally a lot of everything is, you just take a piece out, right to the core. X, Y, and Z, that means it's 3D. Then you have the globe, your Mercator maps, and your projected system. And this is exactly how it works. Most GPS data is recorded and reported using geographic coordinates, particularly here in the United States. We use what we call WGS 1984, which is the World Geodetic System 84. And it's a reference system or datum composed of an ellipsoid, a geoid model, gravitational equipotential surface, EGM 96. Now, remember, elevations can be reported as ellipsoidal heights or orthometric heights. And you can see in this diagram where you have the points measure, the ellipsoid height, the orthometric height. Here's the Earth's surface. Now, when we talk about an ellipsoid, we're actually dealing with an ellipse. You have your global mean sea level, your geoid. Note, orthometric height curves along the gravitational pull, which are often not perpendicular to either the Earth's surface or ellipsoid, but they're perpendicular to the geoid. And that is they're talking about, so if you want to know where the geoid is, this is the geoid height right here. And this is here it is right here. And here's your geoid. Now, when they talk about perpendicular, we're talking about 90 degrees. And here's your orthometric height. It is perpendicular to your geoid. You can see right in the diagram. There are multiple global navigational satellite systems. GPS, again, USA and global. GLONASS, Russia, global. And after 2020, we have your BeiDou, China and global, Galileo, Europe and global. India, France, and Japan are also developing regional systems as well. Now, GPS, the US system, 32 satellites, 20,200 kilometers of altitude, 55 degrees of inclination, 12-hour orbital period, need 4 satellites to be accurate. You have ground control stations. And each satellite passes over a ground monitoring station every 12 hours. And this is exactly what it looks like. You go on a map. Again, this is a satellite. GNSS satellites include almanac and ephemeris data and the signals they transmit. So you have your almanac data, or course orbital parameters for all GPS satellites communicated to your GPS so you can track satellites. Then you have your ephemeris data, or very precise orbital and clock correction for each particular GPS satellite necessary for precise positioning. Again, antennas receive data streams. Gives you your location, your lat and long, your time. Also gives you your errors. Vertical and horizontal. Also, when we measure the range to the satellite, it's a radio signal from satellite. It basically tells the GNSS receiver the satellite clock time and provides the most recent corrections to the satellite's position relative to the Earth. That's ephemeris. Then we also have the GNSS receiver, and that compares multiple satellite times to the receiver time to determine the distance to each satellite. And of course, how the actual location is determined. Well, you have the antenna position. It's basically determined by calculating the distances to at least 4 satellites. This enables the solving for 4 variables, X, Y, Z, and time, which that means it's 4 dimensions using trilateration. So basically, when anything is trilateral, it's triangular, and it includes time. So it's not exactly 4 dimensions. It's 3 dimensions, but time is another unit. Okay, what you have is when you deal with the anatomy of a high precision permanent GNSS station, what you have is you have your GNSS antenna inside of a dome. Then you have a monument solidly attached to the ground with braces. The ground moves, the station moves. Then you have a solar panel for power. Then you have your equipment enclosure, your GNSS receiver, your power, batteries, communication, radio, modem, your data storage, and memory. Now, high precision GNSS requires stable monuments, multiple stations, sophisticated processing, collection of data, and you need to collect lots of data, uses the carrier phrase, dual frequency receivers, high precision orbital information, ephemeris, several years of data. It can be determined by using, the velocities to 1 to 2 millimeters per year. Now, nothing is perfect. You're going to have sources of error. So, some sources of an error. Well, you have your selective availability. That's your ephemeris data encrypted by military. It ended back in 2000. Then you have your satellite orbit irregularities, satellite and receiver clock errors, atmospheric delays. Speed of light is affected by water content and other variables in the atmosphere. And you have multipath, where you have GPS signals. What happens is they can bounce off the ground and then enter the antenna rather than only entering from above. Then you have human error, incorrect base or rover antenna heights, errors, and post-processing, datum and projection errors. Then you have consumer or recreational grade, phones, tablets, watches, hiking devices, 5 meters, no post-processing required. And these are grades of GNSS systems. Again, we're dealing with grades of GNSS systems. As I go by again, we're going to have your consumer recreational grade. That's your phones, your tablets, your watches, your hiking devices, 5 meters. No post processing is required. Then you have your mapping grade. That's your purpose built, GIS enabled. Then you have data collectors, 30 centimeters, post processing correction required. Then you have a survey grade. It's professional tools, longer occupations, static and kinematic devices, 3 millimeters to 2 centimeter precision. Considerable post processing is definitely required. So the precision definitely depends on your system. So looking at this graph, you have your precision of position, and then you have your occupational time or effort required. So you have easy and hard, and here are your different systems, recreational mapping systems, your survey grade, you have your kinematic systems, static, geodetic, campaign systems. And this is your graph right here. It's just giving you the different precise systems. Now, you see this one right here, it's static, 0.005. You're dealing with meters. That is definitely precise. Applications of GNSS. Again, recreational and mapping systems, your phones, your consumer type, your mobile GIS devices. Very inexpensive, low complexity, short occupations, rapid results, low precision systems, kinematic systems. It's your second unit, expensive, moderate complexity, short occupations. Precisions can be rapid or require post processing high precision positions. Then you also have your static systems, very expensive, high complexity, long occupations required, long and complex post processing required, extremely high precision positions, extremely high precision positions. Then again, your tracking position using a recreational system. Again, you can use a phone to track your position during a field day and access quickly the area or position of an object. Again, can quickly assess the area or position of an object. Give that to you again, from the field to the phone to analysis in GPS and GIS. From the field to the phone, that's to analysis in GIS, not GPS, in GIS. So again, with these recreational systems, you can quickly assess the area or position of an object. Number two, creating topography using kinematic systems. Can quickly measure many points with high accuracy and precision. Compare different surfaces to quantify permafrost throw. That's thaw, not throw. Correction. You can compare different surfaces to quantify permafrost thaw in the field to post-process points to surface generation using GIS. See how the system works. And you're really making maps. That's what it is. Example 3, change detection using static systems. Measure a small number of points over a long duration. Can resolve small changes in position. Example, tracking landslides from the field to 4 post-process points to millimeter scale time series. Societal value of GNSS-enabled research. Most people use it for location and navigation, but GNSS-enabled science also provides hazard early warning systems, saving lives, landslide activity, volcano inflation, fault movement, precise measurement of objects, water resources, include aquifers, snowpack, etc., tracking of objects such as organisms, rocks, currents. Without GNSS, we could not know where things are when without directly measuring them. Again, most people use it for location and navigation, but how do Earth scientists use GNSS? Think, pair, share, discussion. Again, how do Earth scientists use GNSS? List as many applications as they can. How do these uses benefit society? Well, they basically categorize each as a direct or indirect benefit. So direct benefits are immediate and they improve lives. Indirect benefits help humans, but are a few steps removed. Most people, again, use it for location and navigation, but how do Earth scientists use GNSS? Well, just gave it to you. Direct and indirect. And that concludes the PowerPoint. So basically, as I sum it up, when we talk about GNSS, we are basically talking about a global navigation satellite system, which is a general term for any satellite-based system that provides autonomous geospatial positioning with global coverage. These systems use a constellation of orbiting satellites to transmit signals that receivers on Earth can use to determine their precise location and time. And of course, I gave you the examples. GNSS includes the US-based GPS, Russian GLONASS, European Galileo, and Chinese BeiDou. Now, how it works, satellite signals, again, satellites in the GNSS constellation transmit signals containing data about their location and the precise time the signal went sent. Receiver measures time. A GNSS receiver on the ground measures the time it takes for the signal to arrive from multiple satellites. Then you have your distance calculation. The receiver calculates the distance to each satellite by multiplying the signal's travel time by the speed of light. Then you have your triliteration. It's by combining the distances from at least 4 different satellites, the receiver can determine its exact position in 3-dimensional space: latitude, longitude, and altitude, and precise time. Common examples, I just mentioned it to you. GPS, Global Positioning System, that's the American system, which is often used as a generic form for GNSS, though it is just one of many systems. Then you have your GLONASS. Your GLONASS is your Globanaya Navigation Naya Sputnikovaya and Systema. That's the Russian navigation system. And you have Galileo, the European navigational system. Then you have your BeiDou or your BeiDou. That's the Chinese navigation system. And then you have your applications. GNSS technology is used in a wide variety of applications, including navigation for cars, boats, and aircraft, location tracking for vehicles, pets, and people, scientific research and surveying. You can also use it for cartography, which that's map making, telecommunications and emergency response, and agriculture for precise field measurement. And what I've done is given you an overview of what GNSS is. You can also use GNSS for streets. If you have Pazer and you're rating streets, you can put those streets that you rated into a system and you can utilize GIS. I know working for the city of Elkhart, that's exactly what happened. There's a system called Pazer that rates streets, and each street that's rated, put right in the system of GIS. And that concludes this topic on GNSS. If you like what I just presented, please comment, share, and subscribe. And if you're looking for some political news and some social content, check out my main channel, the 411 Talk Zone Radio Show channel, right here on YouTube. Now, here's where you can find me. For the 411 Talk Zone Radio Show, you can find me right here on YouTube, X, formerly Twitter, Rumble, and Truth Social. And for the QCIS channel, you can find me right here on YouTube. You can also find me on X, formerly Twitter, and of course, LinkedIn. Once again, thank you for viewing this content on the QCIS channel. On this channel, give you a daily dose of science, technology, engineering, and math. Till next time, my name is Leon Jones. I want you all to have a wonderful and gracious evening. And thank you for viewing this content on GNSS. I will have more videos in the future. Once again, thank you for viewing this content right here on the QCIS channel on GNSS. Again, this is the channel where you get a daily dose of science, technology, engineering, and math. Till next time, my name is Leon Jones. I want you all to have a wonderful and gracious evening.